Hello everybody and welcome. I appreciate you stopping by the channel here at North Country Ham with me, Aaron, KD2RSS. Today's video I'm going to go through and continue with some of my study videos for the extra class license that I'm prepping for. So come study along with me. Alright, thanks for sticking around. Let's get right into this here on continuation of another probably 10 to 15 questions on the current question pool for extra class element 4. Now, the first couple questions we're going to go over, you're going to already see the answer highlighted. That's merely because as I started on this, it stopped recording or failed to record where I had gotten to, and I had noticed it partway through. So we'll go through these first 4 and continue on from there. So let's get right into it here. All right. So I apologize for these first few being spoiled in a way. But what is the purpose of C2 in the circuit shown in figure E7-2? A, it bypasses the rectifier output ripple around D1. B, it is a brute force filter for the output. C, to self-resonate at the hum frequency. Or D, to provide fixed DC bias for Q1. Now this is the diagram it's referring to. You can see C2 here. So C2 provides additional filtering for the ripple frequency. It bypasses voltage changes around D1, the Zener diode, to keep the reference voltage stable. So the correct answer is A. So what is the purpose of C2 in the circuit shown in figure E7, which is right here? It bypasses rectifier output ripple around D1. All right. And we'll move right on to the next question here. What type of circuit is shown in figure E7-2? Now we can see the diagram right there, so it's a little less, not sure what it is, but is it A, switching voltage regulator, B, grounded emitter amplifier, C, linear voltage regulator, or D, monostable multivibrator? Components D1 and Q1 give away the answer. The linear voltage regulator. This should give you a good solid regulated voltage output even though the load current may be changing. So the correct answer is C. So what type of circuit is shown in E7-2? It's a linear voltage regulator. Well, that's kind of flatten it out like that so you can see it a little better. The glare, I'm just kind of real bad tonight for whatever reason. So okay, next question here. What is the purpose of connecting equal value resistors across power supply filter capacitors connected in a series? A, equalize the voltage across each capacitor. B, discharge the capacitors when voltage is removed. C, provide a minimum load on the supply. Or D, all the choices are correct. So those resistors in parallel across the power supply electrolytic filter capacitors help equalize the voltage drops across each of the capacitors, acts as a bleeder resistors when the power supply is turned off, and add a constant load if there is minimal current required out of the power supply circuits. So the correct answer is D. So what is the purpose of connecting equal value resistors across power supply filter capacitors connected in a series? It is all of the answers, and it equalizes the voltage across each capacitor, discharge the capacitors when the voltage is removed, and provide a minimum load on the supply. And we'll move right on here to question number 4 for tonight. What is the purpose of a step-start circuit in a high voltage power supply? A. To provide a dual voltage output for reduced power applications. B. To compensate for variations of the incoming line voltage. C. To allow for remote control of the power supply. Or D. To allow the filter capacitors to charge gradually. So, the modern high voltage power supply likely contains a series resistor and capacitor in parallel in the high voltage plate circuit of the tube in order to buffer the initial inrush of startup current. This allows the filter capacitors to gradually build their charges, minimizing that dreaded arc sound when you turn on a high voltage supply that has been turned off for several years. Some ham operators bring up high voltage on older equipment with a variable AC transformer. So the correct answer is D. So what is the purpose of the step-start circuit in a high voltage power supply? It is D, to allow the filter capacitors to charge gradually. Now that everything seems to be working correctly, we'll continue right on here with the next ones. And they'll be fresh with no highlighter on them this time, since we've got the record working right now. So what is the current in the primary winding of a transformer called if no load is attached to the secondary? A. Magnetizing current. B. Direct current. C. Excitation current. Or D. Stabilizing current. With no load on the secondary of a transformer, the device works essentially as a pure inductor or choke. No power is dissipated except for the resistance of the primary winding and some core for the hysteresis losses, if a core is used. All the current is converted into a magnetic field instead of usable work. So the correct answer is A. So what is the current in the primary winding of a transformer called if no load is attached to the secondary? It is A. Magnetizing current. Boy, are we learning. All right. What is the primary reason that a high frequency switching type high voltage power supply can be both less expensive and lighter in weight than the conventional power supply? A. The inverter design does not require any output filtering. B. It uses a diode bridge rectifier for increased output. C. The frequency inverter design uses much smaller transformers and filter components for the equivalent power output. Or D. It uses large power factor compensation capacitor to recover power from the unused portion of the AC cycle. Conventional heavy-duty power supplies that convert home AC power down to 12 volts DC weigh in at about 2 pounds for every 12 volt DC amp output. Gordo has plenty of 20 amp power supplies that weigh about 40 pounds each. These power supplies are characterized by a huge step-down transformer diode and big filter capacitors. The best efficiency you hope for is about 50%, and they do get warm under load. The newer power supply technology is called switcher. These supplies are lightweight, small in size, and give off little heat, and almost offer 90% efficiency. The output of a switching power supply, whether converting house power down to DC or switching house power up to various higher voltage levels, is clean and pure thanks to high-speed field effect transistors taking the place of that heavy-duty transformer. New switching power supplies have minimal EMI RF interference, and some may even take any detectable emitted spur and let you adjust it out of your favorite listening spot. The switching power supply is about the same cost as the old, bigger transformer supplies, and the very small transformer and filter components easily fit in relatively small packages, whether inside or outside the radio equipment. So the correct answer is C, and you can kind of see the picture of it there, of one of the new switching power supplies. So it says here, high frequency switching power supplies like the one weigh just a couple of pounds. Transformer type power supplies may weigh 10 times as much. But remember to keep inexpensive no-name switchers away from the coax lines and far away from your antenna system, as these produce noise over HF frequencies. Modern name brand switching power supplies are quiet on the HF and UHF VHF frequencies. The Jetstream power supply pictured here is nice and quiet on the HF. So you can see that's one of the newer 30 amp switching power supplies. So what is the primary reason a high frequency switching type power supply voltage can be both less expensive and lighter weight than conventional? The correct answer is C. The high frequency inverter design uses much smaller transformers and filter components for equivalent power output. And that wraps up, appears to be, that chapter on amps and power supplies. Looks like we are about to start Receivers with Great Filters, track number 3 out of the book. So, well, some of the stuff looks a little confusing. We'll go through a few questions on this chapter. Get it kind of prepped here. All right, start right off on a fresh one here. Like the cartoon with the Elmer and that, doing a little CW. So, first question here. What is the term for the suppression in an FM receiver of one signal by another stronger signal on the same frequency? A. Desensitization. B. Cross-modulation interference. C. Capture effect. Or D. Frequency discrimination. A unique property of your FM receiver is the ability to hear only the strongest incoming FM signal. If a distant station is transmitting and a strong local station comes on the air, you'll only hear the local station. The stronger signal is capturing your receiver. The reason AM is still used for on aircraft VHF radio is specifically to avoid the capture effect. Nobody needs to hear everybody else. Or everybody needs to hear everybody else. This is the major use of AM in the VHF world. So your correct answer is C. So what is the term for suppression in an FM receiver of one signal by another stronger signal on the same frequency? It is C. Capture effect. All right. We'll go right on to the next question here on this one. What is the term for the reduction in receiver sensitivity caused by a strong signal near the received frequency? A. Desensitization. B. Quieting. C. Cross-modulation interference. Or D. Squelch gain rollback. If signals mysteriously come in strong, then abruptly get weak, and then come back strong again, Chances are there is somebody nearby transmitting on an adjacent frequency. Their signal is desensitizing your receiver. You can check for adjacent signals with a frequency counter on a spectrum analyzer. So the correct answer is A. So what is the term for reduction in receiver sensitivity caused by a strong signal near the received frequency? Desensitization. A. And don't ask me why I'm struggling to say that word. Alright. Gonna continue on here. Which of the following reduces the likelihood of receiver desensitization? A decrease in RF bandwidth of your receiver. B. Raise the receiver IF frequency. C. Increase the receiver front end gain. Or D. Switch from fast AGC to slow AGC. If you have a large HF, VHF, UHF base station transceiver, you'll notice that the insides are all enclosed in tiny metal cans. This shielding is necessary to keep the receiver from desensitizing on the band when you are transmitting on another band. Shielding is a good way to minimize internal desensitization. Desensitization occurs when the nearby signals get into your receiver and cause the gain to be reduced. By decreasing the RF bandwidth on a receiver, you reduce the likelihood of nearby signals affecting the receiver. Only signals that are within the passband of an RF are likely to have effect. So which of the following reduces the likelihood of receiver desensitization? Correct answer is A. Decrease the RF bandwidth of the receiver. Okay. What is the frequency discriminator stage in an FM receiver? A. An FM generator circuit. B. A circuit for filtering two closely adjacent signals. C. An automatic band switching circuit. D. A circuit for detecting FM signals. Anytime you see the words frequency discriminator, you know that you are dealing with the signal detection or demodulation in an FM transceiver. So the correct answer is D. So what is the frequency discriminator stage in an FM receiver? Correct answer D. A circuit for detecting FM signals. All right, kind of move right along here onto our next one. Why is de-emphasis commonly used in FM communications receivers? A. For compatibility with transmitters using phase modulation. B. To reduce impulse noise reception. C. For higher efficiency. Or D. To remove third-order distortion products. The emphasis in an FM receiver rolls off and attenuates the higher modulating frequency response. This compensates for the FM transmitter using phase modulation, where the transmitter rolls off the lower frequencies. This provides compatibility in the FM communication system. Answer is A, and it kind of shows the de-emphasis circuit. So why is de-emphasis commonly used in FM communications receivers? A. For compatibility with transmitters using phase modulation. All right, we'll do this question on this page and we'll end it there. So for the last question for the night, what transmitter frequencies would cause intermodulation product signal in a receiver tuned to 146.70 megahertz when the nearby station transmits on 146.52 megahertz? A. 146.34 megahertz and 146.61 megahertz. C, 146.88 megahertz and 146.34 megahertz. C, 146.10 and 147.30. Or D, 173.35 and 139.40. To calculate the possible sources of an intermodulation interference, we check for the signals that lead to this type of problem that are commonly at base and repeater stations. These are 4 calculations to find the intermodulation frequency that could be causing the problem. 2 that add frequencies and 2 that subtract the frequencies. The subtracted calculations are the only ones that produce frequencies close enough to cause significant interference. As the question states, the intermodulation product, FIMD, I don't know if you can make it out on here, it's pretty small, is received on 146.70 megahertz when the signal at 146.52 is transmitted. These calculations, when the frequencies are subtracted, are IMD2 equals 2F1 minus F2. FIMD4 equals 2F2 minus F1. And then it's rearranging. You've got a few others here. F2 equals 2F1 minus FIMD2. F2 equals 2 times 146.52 minus 146.70. So F2 equals 146.34 megahertz. And then doing the math over here, it comes to 146.61 megahertz. So the correct answer is A. So what transmitter frequencies would cause intermodulation product signal in a receiver tuned to 146.70 when the nearby station transmits on 146.52? It would be A, 146.34 megahertz and 146.61. So because both are smaller than the 2 frequencies, that's where, think about it that way. They've subtracted basically from both frequencies. You know what, let's just do these last 2 on this page and that'll wrap up first couple of pages in there. So, next question here. Which of the following describes problems caused by poor dynamic range in a receiver? A, spurious signals caused by cross-modulation and desensitization from strong adjacent signals. B, oscillator inability requiring frequent returning and loss of ability to recover the opposite sideband. C, cross-modulation of the desired signal and insufficient audio power to operate the speaker. Or D, oscillator inability and severe audio distortion of all but the strongest received signals. In a receiver that does not have good dynamic range, cross-modulation of the desired signal can be encountered, and the receiver can be desensitized by strong adjacent frequency signals. So the correct answer is A. So which of the following describes problems caused by poor dynamic range in a receiver? Answer is A, spurious signals caused by cross-modulation and desensitization from strong adjacent signals. And last question for tonight, serious this time. What does a receiver noise floor of minus 174 dBm represent? A, the minimum detectable signal as a function of received frequency. B, the theoretical noise on a 1 Hz bandwidth at the input of a perfect receiver at room temperature. C, the noise figure of a 1 Hz bandwidth receiver. Or D, the galactic noise contribution to minimal detectable signal. Noise occurs at any time objects are warmed above absolute zero. If you had a perfect receiver with no internal noise, it would still detect noise when connected to an antenna. At room temperature, that noise level is about minus 174 dBm for every 1 hertz of bandwidth. In addition to the natural noise, man-made noise also occurs and is much more prevalent at some frequencies than others. On HF bands, man-made noise is so common that a receiver with very good noise floor is not nearly as important as it would be for a receiver at 10 gigahertz trying to detect EME signal. So the correct answer is B. So what does a receiver noise floor of minus 174 dBm represent? Correct answer is B. The theoretical noise on a 1 hertz bandwidth at the input of perfect receiver at room temperature. All right. Well, that was some good study questions tonight, and it feels pretty good moving right along into the next chapter also. So I appreciate everybody kind of coming along with me, and I hope it's helping you as much as it's kind of helping me by going over the questions like we are. It helps it kind of stick in the noggin here a little bit. So get some other projects that I'm kind of tinkering on. I'm still working on the automated satellite tracking system. That's kind of probably between 95-98% operational. We're basically got everything all together and in a testing phase, trying out the sketches on the Arduino stuff, trying to use one of the ones that we found online that seen some other videos on, trying to use that sketch a little bit as a testing platform with some of the setup, as well as continually working on our own sketch that a friend of mine from the local club and I are doing. So we're tinkering with it a little bit today, got some more headroom on there, got it kind of trying to talk and communicate and work. So we're getting there. So hopefully the goal is to have something up and running and operational by field day. So it's looking pretty good there. So I hope everybody's doing well, and we'll see y'all on the next one. With that, I'll say 7-3 and get on the air.